It's 3:47 a.m. local time, and something impossible is happening in Russia. 4 objects are racing toward Moscow at 380 kilometers per hour, completely invisible to the most sophisticated air defense network on Earth. They shouldn't exist. The S-400 radar operator outside Ryazan was staring at his screen, watching what looked like a flock of birds. Except birds don't fly in perfect formation, and birds definitely don't fly straight toward Russia's largest oil refinery. At exactly 52 kilometers from the target and 27 kilometers from the S-400 battery, the lead Beaver drones climbed sharply to 800 meters. A missile would need 27 seconds to reach them, but at emergency power, the drones could reach the 2-kilometer defensive dead zone in 41 seconds. That gave the battery commander just 14 seconds to decide whether these were real threats or decoys. His thought process went something like this. Each missile costs $2 million. 10 seconds left. But the closure rate was real. 7 seconds. His training said to wait for positive identification. 5 seconds. But if these were real, he fired. 2 48N6DM interceptors roared from their tubes, accelerating to Mach 6 in 3 seconds. But watch what the drums did. They immediately dove back to 200 meters, vanishing below the radar horizon. Here's the problem. These missiles use semi-active radar homing. They don't have their own radar. They need the ground station to continuously paint the target with radar energy. Without that illumination, they're blind. The commander could only watch his screen in horror. His missiles were trying to predict where the targets went, but their onboard computers only had the last known position. They detonated 80 meters above where the drones had been. Close enough that the 180-kilogram fragmentation warhead sent 24,000 steel fragments into empty air, but not close enough to matter. Now, the refinery's last line of defense, 2 Panzer S-1 batteries, had exactly 17 seconds to acquire and engage. But the Panzer's 1RS-21E radar operates on the UHF and EHF bands and is optimized for larger targets. Against 0.1 square meter drones at 8 kilometers, the signal return was barely above background noise. 12 seconds left. The operators saw intermittent contacts flickering in and out. 8 seconds. They tried to slew their 2 A38M cannons, but the hydraulic traverse takes 3.2 seconds to rotate 180 degrees. 4 seconds. By now, the lead beater had already identified its target. The first warhead struck at 3:52 a.m., but this was just the first strike. 3 more Beavers hit 3 more targets in sequence. The cascade consumed 140,000 tons of petroleum. Within 90 seconds, the entire western section was an inferno, reaching 1,200 degrees centigrade. It would burn for 72 hours. Moscow's fuel supply had just been cut by 40%. And this was only the beginning. 470 kilometers away, 12 more drones were approaching their target. This time, the Russians thought they were ready. They weren't. While the drones were still impacting the previous target, the Panzer S-1 batteries at the Novy Orengoy refinery had been tracking the incoming threat for 11 minutes. 3 batteries were arranged in a triangular formation with overlapping fields of fire. Each system's 1RS-21E radar could track 20 targets and engage 4 simultaneously at ranges up to 20 kilometers. The battery commanders had studied Ukrainian tactics. These drones would never reach their target, or so they thought. At 4:03 a.m., something strange happened. 4 of the 12 drones suddenly climbed to 500 meters, exposing themselves completely. Then, the radar classification system screamed a priority alert that changed everything. The radar return signatures had transformed. The aspect ratio, speed, and radar frequency response now matched Kh-101 cruise missiles. Here's what was really happening. The climbing drones had deployed corner reflectors, triangular pieces of aluminum that create retroreflection. When radar hits them, the signal bounces back at exactly 180 degrees with amplification. A 10-centimeter reflector can create the same radar return as a 10-square-meter object. The Panzer's computer saw cruise missiles because that's exactly what the reflectors were designed to mimic. The lead battery commander had 2 seconds to decide. His engagement protocol was clear. Cruise missiles are priority targets, always. His training took over. 8 5.7E6 missiles launched in 12 seconds, each accelerating to 1,300 meters per second. The missiles used command guidance for the first 18 kilometers, then switched to semi-active homing. But something was wrong. These cruise missiles were pulling 9G turns, impossible for a Kh-101 which breaks apart at 3Gs. And they were multiplying. 4 became 8, 8 became 16. Watch what's really happening here. Each drone was dropping reflectors at 2-second intervals. The radar saw new targets appearing while the old ones descended slowly. $3 million in missiles were chasing aluminum foil that cost less than your morning coffee. But where were the other 8 drones? The answer came from his worst nightmare. Behind him.
While everyone watched the fireworks at 1,500 meters, 8 UJ-22 drones had approached from the opposite direction at just 50 meters altitude. The Panzer's fatal weakness is its phased array radar. It is fixed. It can electronically steer the beam 45 degrees left or right, but to look behind requires physically rotating the entire 30,000 kilogram turret. That takes 4.7 seconds. The commander screamed the order, "Traverse now." Too late. The drones were inside 1.2 kilometers. The 57E6 missiles need 1.5 seconds to arm their proximity fuses after launch. At this range, they'd impact before arming. Only the twin 30mm cannons remained. The two A38M guns opened fire, each barrel firing 2,500 rounds per minute. The computer calculated the lead angle. At 200 kilometers per hour perpendicular crossing, that's 31 mils. The UJ-22s were programmed for this exact scenario. Every 2 seconds, they executed dynamic altitude variation, random changes between 40 and 80 meters using barometric altimeters. The Panzer's fire control computer uses predictive targeting, calculating where the target will be in 0.8 seconds when the rounds arrive. But with random altitude changes, prediction becomes probability. The hit probability dropped from 83% to 31%. One drone flew straight into the cannon stream and disintegrated 300 meters from impact, but 7 made it through. 3 of them found the target. And that's when the third group struck.
All 3 Panzer batteries were reloading. The 57E6 missiles are stored in tubes below the turret. The automatic loader extracts spent tubes, fetches fresh missiles, and rams them into launch position. This takes 90 seconds. 90 seconds of complete vulnerability. The refinery took 3 more direct hits. The Ukrainian planners had calculated every second, knowing exactly when the Russians would be defenseless. But at the next target, Russia had just deployed something the Ukrainians hadn't detected yet. At 4:18 a.m., 6 UJ-22 Beavers approaching Voronezh suddenly went blind. GPS signals gone, communications dead. Navigation screens showed only static. A Krasuka 4 electronic warfare vehicle had just activated. This wasn't ordinary jamming. The Krasuka 4 floods the electromagnetic spectrum from 0.1 to 18 gigahertz with 500 watts of directed power. To understand this, consider GPS signals. They transmit at 0.025 watts from satellites 20,000 kilometers away. The Krasuka's jamming is, at this range, billions of times stronger than the GPS signal. It's like trying to hear a whisper while standing inside a jet engine. The drones automatically switch to inertial navigation using their gyroscopes. But these gyroscopes drift, accumulating an error of roughly 1 to 2 kilometers per hour of flight. After flying 380 kilometers for 68 minutes, the accumulated error meant they could miss by over a kilometer, and missing meant complete failure. The lead drone's processor was now in full crisis mode. At 95 degrees Celsius, it began thermal throttling, reducing clock speed to prevent damage. But slower processing meant fewer terrain pattern matches per second. The drone began emergency load shedding. Navigation lights off, saving 2 watts, telemetry transmitter off, saving 5 watts, radar warning receiver off, saving 3 watts. Every watt saved meant 0.5 degrees Celsius cooler. Every degree meant 100 megahertz faster processing. 30 seconds to impact, still no terrain match. The algorithm was failing. 20 seconds, processor at 98 degrees Celsius. 10 seconds, thermal shutdown imminent. 8 seconds, the pattern locked. Not on the fuel tanks themselves, their shadows were shifting and useless, but 3 tanks created a unique, fixed geometric relationship. The intersection points of their long, stationary shadows formed a triangle with specific, unchanging angles. Tank 7 was identified with 4 meters to spare. But this targeting solution was trapped in one drone's computer. The Krasuka's jamming made communication impossible. Unless the lead beaver tried something desperate, frequency hopping spread spectrum, transmitting on 1,000 different frequencies per second in a pseudo-random pattern. The Krasuka can't jam all frequencies simultaneously with equal power. On channel 847 for 1 microsecond, there was a gap. The drone transmitted 128 bytes, just GPS coordinates and impact timing. The other 5 drones received the fragment through matched filtering and adjusted their course. Tank 7 took the first hit at 4:20 a.m. The warhead struck exactly where steel meets concrete, the weakest point due to differential thermal expansion. The fuel lake ignited. The Krasuka 4 crew watched the wall of fire advancing at 30 meters per second. They abandoned their $20 million vehicle and ran. As the jamming cleared, 8 more drones appeared on radar screens. They were heading for Russia's most heavily defended military target. The Russians were about to learn that impossible was just Ukrainian for challenge accepted. Primorsko-Akhtarsk military airfield was a fortress. 4 Tor M2 air defense vehicles were arranged in a perfect diamond formation with 5-kilometer spacing. Each section provided overlapping coverage with no gaps.
Two Su-35 fighters circled overhead at 8,000 meters. Every radar was active: search, track, and fire control. The base commander had studied every Ukrainian attack, positioning his defenses using computer modeling. 8 drones against this meant a guaranteed shootdown. But the Ukrainians knew something the Russians didn't. Watch what the 8 UJ-22s are doing. They're not flying straight. This snake pattern, technically called a sinusoidal trajectory variation, wastes fuel. It adds 8% to the flight distance, burning 4.3 extra liters in a one-way mission where every drop matters. Why? Because the Tuapse uses command guidance with predicted intercept points. Each weave forces the system to recalculate. The fire control computer models target motion using common filtering. But common filters assume consistent behavior. Random weaving introduces what's called process noise, artificial uncertainty that degrades the prediction. With each unpredictable turn, the error ellipse for the missile's predicted intercept point grows larger. The system has to fire more missiles to cover the expanded area of possible locations, draining its limited ready ammunition. This was a battle of algorithms, fought not just in the sky, but inside the fire control computers. The drones were not trying to outrun the missiles, they were trying to outcalculate them.
Small errors compound. By the moment of missile launch, the accumulated error could reach 50 meters. At 4:32 a.m. exactly, all 4 Tor M2 systems fired simultaneously. 16 9M338 missiles accelerated to Mach 2.5 using solid rocket motors, producing 4,000 kilograms of thrust. The missiles used 3-stage guidance: inertial for the first 2 seconds, command guidance until 2 kilometers from the target, then active radar for terminal homing. Their trajectories formed a kinematic engagement box, no escape. 10 seconds until impact. The missiles were closing at 850 meters per second. 9 seconds. Terminal guidance activated. 8 seconds. The seekers acquired their targets. Then the impossible happened. The UJ-22s went vertical, not a gentle climb, but a 6G pull-up that took them from 180 meters to 1,200 meters in 4 seconds. The missiles tried to follow, but couldn't. The 9M338 uses aerodynamic control with 4 canards. At the required climb angle of 76 degrees, the canards stalled. Stall means the airflow separates from the control surface. No airflow, no control. The missile's thrust vector control could only compensate for 12 degrees. They sailed harmlessly below their targets. Except one. Its proximity fuse detected an infrared signature above, the drone's 400 degrees Celsius exhaust plume. The warhead detonated, launching 3,500 tungsten cubes in a directed pattern. The drone became confetti. But that spectacular interception served a purpose. Every eye, every radar, every weapon was looking up. Nobody saw what was approaching from the sea. 4 UJ-26 Beavers crossed the beach 15 seconds later. They had flown 700 kilometers over the Sea of Azov at just 5 meters altitude. For 2 hours, they'd used radar altimeters to maintain height above the waves. The altimeters work by timing radio pulses, but seawater reflects differently than land. They had to constantly recalibrate, but the ocean route meant 0 radar coverage. Ground-based radar can't see beyond the horizon, and the horizon at 5 meters altitude is only 8 kilometers away. The Shahed storage hangars were completely undefended. Inside Hangar 2, 30 Shahed 136 drones sat in maintenance cradles. Each Shahed carried a warhead with 40 kilograms of composition C4, RDX with plasticizers. Each had 50 liters of fuel. Do the math. 1,200 kilograms of explosive plus 1,500 liters of fuel in a 40-meter space. That's 30 kilograms of explosive per square meter, 10 times the NATO standard for ammunition storage. The first Beaver struck Hangar 2's roof. The hangar didn't explode, it launched. It reached 50 meters altitude before gravity reclaimed it. Hangar 3 went 1.3 seconds later. Hangar 4 followed. In 45 seconds, over 200 Shaheds worth $6 million were vaporized. The base commander ordered an emergency scramble, but the runway was obscured by smoke from the burning drone frames. Visibility, 150 meters. Minimum for Su-35 takeoff, 200 meters. Primorsko-Akhtarsk, Russia's primary Shahed base, was eliminated, and the longest shot was still to come. This time, the drones would face something they couldn't outmaneuver. At 4:44 a.m., two modified UJ-26 Beavers reached Penza, 630 kilometers inside Russian territory. This should have been impossible. The standard Beaver range is 350 kilometers, but these weren't standard. The modification was ingenious. Auxiliary fuel tanks in the warhead bay. They sacrificed 5 kilograms of explosive, reducing the warhead to 20 to 15 kilograms, but gained 12 liters of fuel. That extended the range to 980 kilometers with 30 minutes reserve. Unknown to them, an Su-35 had been hunting for 20 minutes. The pilot was following close behind. His Airbus E radar was in a narrow beam mode, a 10-degree scan at 20 kilowatt power. This created a high-power aperture product, concentrating energy for maximum detection range against the 0.1 square meter drones. He achieved a solid track at 43 kilometers. The Beavers had nothing. No chaff, no flares, no jammers. That left only one option. The pilot selected 2 R-77 missiles and fired. These aren't ordinary missiles. They use active radar homing with their own seekers. Once launched, they're completely autonomous. The pilot fired at 18 kilometers and immediately executed a 180-degree turn. His job was done. Now it was the missile's turn. The R-77s accelerated to Mach 4 using solid rocket motors. They would cover 18 kilometers in 13.2 seconds. At 12 kilometers, the seekers went active. Each seeker could track targets pulling up to 12 Gs. The drones could manage a maximum of 6 Gs, but they could do something the missile could not: execute barrel rolls while varying altitude by 150 meters. The idea was to create an angular velocity that exceeded the missile's control response. The R-77's control system updates at 100 times per second. The drones were changing direction at 150 degrees per second. This created what's called gimbal lock. The seeker physically couldn't rotate fast enough to maintain its lock. The first R-77's proximity fuse triggered at 80 meters. Hundreds of 8mm tungsten balls traveling at 2,100 meters per second perforated the Beaver's fuselage. Its control surfaces locked at random angles. Half of its vertical stabilizer was gone, but the engine kept running. The second missile didn't miss. A direct impact converted one Beaver into aluminum confetti, but its damaged wingman wobbled onward. The drone's flight computer calculated impact in 40 seconds. Its current trajectory would miss building 3 by 40 meters, unless something changed. Now, final 3 seconds. Maximum thrust pulse. 30 meters off target. 20 meters. 10 meters. Impact at 0464 hours. The Beaver crashed through the roof at 73 meters per second. Under normal circumstances, 15 kilograms of explosive wouldn't devastate an industrial building, but semiconductor fabrication is different. The clean room's air filters, designed for 0.3 micron particles, were instantly overwhelmed by millions of concrete and metal fragments. The electron beam lithography system, worth $47 million, requiring 18 months to install and calibrate, was destroyed. The ion implantation equipment vaporized. 6 months of military processor inventory became silicon dust. Russian military chip production was paralyzed for a minimum of 6 months. Within 6 hours, Russia would begin the largest air defense redeployment of the war. Every system moved to protect refineries meant a gap in battlefield coverage. Each gap meant Ukrainian HIMARS could operate freely. Ukraine had spent $412,000 in drones to inflict tens of millions of dollars in damage. But the real victory wasn't monetary, it was psychological. If Ukrainian drones could reach Penza, 630 kilometers from the border, they could reach anywhere.